we're going to look at the graphs of this function and its inverse. And I left the inverse in this notation instead of writing it as x over 2 minus 1/2 because I think it's a little easier when finding the ordered pairs to use this. So just know that they are the same exact thing. All right, so I picked arbitrary x's. Arbitrary means these aren't special for any reasons. I just picked -2, 0, 2, 4. I could have picked 1,000, it's just I don't want to go out to 1,000 on my graph. So I just picked kind of convenient numbers that fit right here on this graph. So let's find these outputs. So when I input -2 into this function, this would output f of -2. Now we have the function, so let's find that number. So 2 times -2 is -4, plus 1 is -3. So I'll write what I'm doing, and this is going to be in blue on this graph. So it's going to be 2 times -2 plus 1, which ultimately means the output is -3. Okay, now we'll do the same thing for 0. 2 times 0 plus 1 is 1. 2 times 2 plus 1 is 5. 2 times 4 plus 1 is 9. All right, so I'm going to graph that, and I'm going to do the best I can to make this proportional, but it might look a little bit off. The dots might not exactly line up. You just have to bear with me. So -2, -3 is the first point. So -2, -3 is my first point. Okay, and I said I was going to do this in blue. I'll do this in blue. Okay, 0, 1. So 0, 1's there. 2, 5. Right there. And 4, 9. All right, sorry, got interrupted there. So you see, here's my line. So this is the graph of f of x, all right, of 2x plus 1. That's what the relationship between the x and y's looks like. It looks like a line, hence the name linear function. All right, now, if the inverse function does what I say it did on the previous board, what should happen is if I plug in -3 to the inverse, the output should be -2. Let's see if that happens, and I'll do this in red. So -3, I'm going to input into this function. So I'm going to have -3 minus 1 divided by 2. And that is equal to -4 divided by 2, which is -2. It worked for that one. So let's try it again. I'm going to input 1 for my input, and my output should be 0. So let's see if that happens. We have 1 minus 1 over 2, which is equal to 0. So it works again. Let's try it again. 5. I have 5 minus 1 over 2 is 2, because 5 minus 1 is 4. 4 divided by 2 is 2. Finally, 9. 9 minus 1 divided by 2 is 4. 9 minus 1 is 8. Divided by 2 is 4. Now you might say, you just chose these numbers because you know that would happen. No, I know the math, and I know what inverse functions do. Okay? So, no matter what x and y you would pick, or what x you would pick, and then pair it with a y for f of x, it would be the exact opposite for the inverse. All right, so let's plot these points and see what happens. So we have -3, -2. -3, -2. Okay? 1, 0. Okay? 5, 2. So there's 5, there's 2. Okay, and then the last one is 9, 4. So 6, 7, 8, 9, and 4 would be about here, or about here. Okay, didn't do so well in this one. I'm going to try and connect them with a line. So that's how you fudge it. Make this dot bigger. All right, and there's the inverse. So here's where knowing some geometry comes into play. You should see that there's some symmetry going on. Okay, and in geometry, you study symmetry in which the x and y's are switched. Okay, and what this is a reflection. It's not a reflection over the x or the y axis, it's a reflection over a line. And that line is the line y equals x. Okay, so inverses, and I'm going to write this, you should write this in your notes as well. Inverses are reflections over the line y equals x. Okay, so if you're given two graphs and you want to know, are they a reflection of each other? Okay, well, all you got to do is see if it's a reflection across this line y equals x. Okay, or pick points along each graph and see if they're switched. So that's a little bit about inverses from a graph. I'll follow with some more examples for you. All right, so we need to find the inverse of each function. All right, so we're going back to the three-step process that I talked about earlier in the video. So, step 1, switch, or actually replace f of x with y. Okay, next step, do it in a different color, switch x and y. And finally, solve for y. So in solving for y, you would subtract 8 from both sides. So you get x minus 8 is equal to 4y. Then divide both sides by 4. And you get y is equal to, and I'm going to write it as two separate terms. So I'm going to have 1/4 x minus 8 divided by 4 is 2. And then I'm going to write it as an inverse, in inverse notation. So the inverse of f is equal to 1/4 x minus 2. Okay, and that problem is done. Now next problem. Again, replace f of x with y. Second step, switch x and y. Third step, solve for y. Okay, so the first step would be subtracting 16 from both sides. So we have x minus 16 is equal to negative 1/4 y. Now here's a habit I want us to get into. I want us to get used to the habit of, instead of saying negative 1/4 times y and saying, oh, I'm going to divide because that's the inverse operation. When you divide by negative 1/4, The rules of fraction says when you're dividing by a fraction, you multiply by the reciprocal of that fraction. So I'm going to skip that, and I'm going to say, no, what I'm going to do is I'm going to multiply both sides by the reciprocal, because that's what I'm going to do anyways if I divide by a fraction. Okay, so the reciprocal of negative 1/4 is negative 4. So I'm multiplying by negative 4. I don't want to put just minus 4 there. It might look like I'm subtracting 4. And now, since this side has two terms, okay, I can't just multiply one or the other by negative 4. I need to multiply this whole side by negative 4. Okay? So now, these cancel out to just be y. And then I have to use the distributive property on the left side. So we have negative 4 times x, which is negative 4x. Negative 4 times negative 16 is a positive 64. And now I have y by itself. So I finished the problem by doing the inverse notation. So I'm going to have the inverse of f of x is equal to negative 4x plus 64. All right, and then the last example. So I'm going to have y equals 2/3 x minus 8. Switch x and y. So I'm going to have x is equal to 2/3 y minus 8. Next step, add 8 because I'm trying to isolate y. So I'd have x plus 8 is equal to 2/3 y. Again, I have a fraction. So I'm not going to divide by a fraction. I'm going to multiply by its reciprocal. So the reciprocal of 2/3 is 3/2. Okay? So what I'm going to end up with, these cancel, so I have y, I've isolated y. Now I need to distribute here. 3/2 times x is 3/2 x. Okay? 3/2 times 8, well, this is like 8/1, and when you're multiplying a fraction by another fraction, I've made this 8 now a fraction by putting it over 1. Multiply numerator times numerator, so 3 times 8 is 24. And 2 times 1 is 2. So, before I say that's my final answer, I have to ask, can that be reduced? Well, this just says 24 divided by 2, which is 12. So there's our answer. We just need to write it in the correct inverse notation. So my final answer is the inverse of f of x is equal to 3/2 x plus 12. And that's how you find the inverse of a linear function. All right, a closing thought on inverses. And this is kind of the advanced kind of way of thinking, and I want you guys to get there. Because the other stuff is very procedural. Do this step, do this step, do this step. The advanced is kind of digging deeper and thinking more deeply about these topics. So, let's say we have this graph here. First off, without me naming it, is this relation a function? Is every x paired with only one y? Okay, well, we can use the vertical line test and say, yeah, well, it passes the vertical line test. These don't get all the way vertical. So since it passes the vertical line test, it is in fact a function. So the question is, if I take the inverse of this function, is it always going to be a function itself? Is the inverse graph going to be a function? Is it still going to pass the vertical line test? So I want to explore that a little bit. So here I have some ordered pairs that lie on this graph. I'm not going to even tell you, it doesn't even matter what the function is. If you remember some Algebra 1, you could probably guess what it is. But here are some ordered pairs that will lie on this graph. All right, so what can we do to see if the inverse is a function? Well, we can look at a table of the inverse using this table. How can we do that? All we have to do is switch the x's and y's. So we have 4, -2, 1, -1, 0, 0 stays. These two switch, and it looks like it stays the same, but it doesn't. And then we have 4, 2. So I ask from here, can you tell if this is a function or not? Is every x paired to only one y? And the answer is no. It's no longer a function because look, we have 4 and 4 here, and it's matched with -2 and 2. We have 1 here, it's matched to -1 and 1. So it's no longer considered a function. It could still be an inverse. We could still find an equation for this thing. And we'll do that later on in the year. However, it doesn't necessarily mean that it's going to be a function just because it has an equation. Okay? So, let's look at the graph. What might the graph look like? Well, again, if we're going to reflect over this line, it's easier to see this with patty paper. Hopefully you remember that from geometry. But it's going to look like this. Okay? And if we do the vertical line test on this red graph, it fails. It fails here and here. So it fails the vertical line test, so it's not a function. So the question is, can we determine from an original graph whether its inverse is going to be a function? And it turns out we can. And that is called the horizontal line test. So if you do the horizontal line test to a function you're given, if one horizontal line or multiple horizontal lines cross the graph at more than one point, then its inverse is not a function. Okay? It doesn't mean that this is not a function, because that'd be the vertical line test. It means that its inverse is not going to be a function. And let's think about why that might happen. What happens to vertical lines when you take the inverse? Not vertical lines, horizontal lines, excuse me. What happens when you take horizontal lines on an inverse? Well, those horizontal lines, the x and y switch places. So this is an equation in the form of y equals some number. So it becomes x equals some number. So if it fails this test, it's going to fail the vertical line test on its inverse. All right, so that's the deeper thought. Is this horizontal line test, and it's a way to test if a function's inverse is a function. Good luck on your work, and let me know if you have questions.